Now the factors that we'll see now, temperature and catalyst, these are factors that will affect energy. So let's look at temperature. Now, as you know, temperature relates to the average kinetic energy of the particle. So when temperature is increasing, you have particles that have higher average kinetic energy. So if we consider this Maxwell-Boltzmann curve over here, this line, this indicates the activation energy. And the first curve over here, this is showing the energy of the particles at 0 degrees. So at 0 degrees Celsius, you can see that the majority of the particles have this kinetic energy. Let's put it KE1, right? As we're increasing the temperature, let's say we move to 25 degrees Celsius, we now see that the majority of the particles have this kinetic energy. This is the peak, so this is kinetic energy 2. And at 100 degrees Celsius, let's say here, at 100 degrees Celsius, majority of particles have this kinetic energy 3. Right, so as you can see, the peak of the curve, so this is the peak of the curve, is moving to the right as temperature is increasing. Now, if you look at the graph, you'll see that at 0 degrees, the maximum kinetic energy of the particles, that is the peak of the curve, which is the maximum kinetic energy here. This is arbitrary value 10. The values don't really mean anything. They have no units for now. It's just showing you the values on a scale. So just so you can see what's happening to the values. Now, if you look at 25 degrees Celsius, the maximum kinetic energy here is at 15. And for 100 degrees Celsius, you can see that the maximum kinetic energy is at 20. So as temperature increases, the maximum kinetic energy of the particles increase, which is in line with what we have learned, that as temperature increases, particles move faster. Now, the second thing about this Maxwell-Boltzmann curve is that you see there is a difference in, like, the area seems different. So you can see this area over here. This area over here seems different. However, if we look at the area under the curve, let's look at this part over here, under 10 degrees Celsius, the total area under the three curves should stay the same. So the area under the 0 degrees curve, the area under the 25 degrees curve, and the area under the 100 degrees curve should be the same. So the area under the curves actually represent the total number of particles in the sample. So the total number of the particles in the sample stays the same. So the area under the curve should stay the same. The line, that bold line over here, represents the activation energy required for the reaction to occur. Now, the areas shaded here, blue, green, and yellow, that you can see here, the areas under the curve over here represent the number of particles with energy greater than activation energy. So all these particles actually have energy less than activation energy. So the probability of them colliding successfully is minimal, while these particles, they have energy higher than activation energy. Therefore, when they collide, the probability of the reaction being successful is more. Now, if you look at the area under the curve, the blue part here, this is the smallest. So here you have the smallest number of particles with energy greater than activation energy. The green part, actually the green part should have been like this, should have been the whole thing here. And you can see that this area is more than the area at 10 degrees Celsius. So the area under the curve above activation energy is going to be more when temperature increases. And if we look at the yellow part over here, that yellow part over here, that area actually should have been like this, the whole thing here. So this yellow area here, it shows the proportion of particles with energy greater than activation energy. So at 100 degrees Celsius, you have the most number of particles with energy greater than activation energy. So this is why at higher energy, you're going to have more rate of reaction increases. Now, as you're showing the Boltzmann distribution curve with temperature, there's a few things that you need to note. So let's say the examiner asks you to draw the Maxwell-Boltzmann curve at two different temperatures. So the first thing is that you have to get your axes right. This should be number of particles. You could also write fraction of particles or fraction of molecules. Here you're going to have kinetic energy, or it's simply just energy. And when you're drawing the first curve, so it should start at the origin. It should not be symmetrical, and it should look like that. The shape should be like this. And you're going to mention the activation energy, EA, which shows activation energy. So you can show it like this. Now, this is T1. Now, at a higher temperature, let's say at T2, high temperature, the peak is going to be lower. See, the peak gets lower. So I'm going to have a lower peak, plus the peak should shift to the right, because as temperature increases, maximum kinetic energy of particles increase. So if here for T1, the maximum kinetic energy was here, for T2, the maximum kinetic energy is going to be here, right? So you see it's going to shift to the right, and it's going to be lower. Let's say here. Okay, so peak should shift to the right and should be lower. The third thing that you have to be careful is that approximately the overall area should stay the same. So the overall area is the same. Peak is lower. Peak has shifted to the right. And of course, you'll see that over here, it does not meet the x-axis. It will not meet the x-axis, of course. And you can see that the number of particles with kinetic energy greater than the activation energy is higher for the graph under T2. Another thing that you have to pay attention as you're drawing the curve, make sure that when you're drawing the curve, it's not, you're not drawing symmetrical curves, which means that you're not drawing something like this, and then the second curve is going to be like this. These are symmetrical curves, and you can see they meet at 0 as well. So this is wrong. Even if it shifts at lower, even if the peak is lower and if it shifts to the right, these are symmetrical curves. So these are wrong. So you see, at high temperature, number of particles with energy greater than activation energy increases, rate of collision increases, there is an increase in number of successful collisions, and normally the rate of reaction doubles for every 10 degrees rise in temperature.